this and puts a little bit more clarity to what we've been kind of hinting around at, right? So we talked about initially with Dalton's theory that matter is composed of atoms, and when matter undergoes a chemical change, those atoms that make up that matter, they rearrange, right? You don't lose them, you don't destroy them, they just get rearranged. And we talked about how elements are only composed of one type of atom, and every atom within an element has the same chemical properties, right? And that an element is only one type of atom, and every one of those atoms is going to do the exact same thing that the other ones do, no matter what. All right. And so when we talked about the just the idea of atoms, that all of that was hypothetical. You know, when we talk about in the 5th century BC, when you had Greek philosophers talking about that thing matter being made up of things that are indivisible, that are small particles that are they had no way of knowing that. That was just a hypothesis. And so Dalton was able to take that hypothesis and test it, and that's how he developed these different tenets of his theory. So the third part is let me hold on one second. All right, so the third part of his Dalton's atomic theory is that atoms of one element differ in properties from other elements. I mean, that's a no-brainer, right? I'm just going to shorten this down. Right? So the properties of atoms that make up sodium are different from the properties of the atoms that make up magnesium, right? So if you have a sodium atom versus a magnesium atom, the sodium atom or the element sodium versus the element magnesium, the atoms are going to behave totally differently. Than magnesium, all right? And again, that kind of ties into the second one that says that all the atoms of a particular element have the same properties. So it goes without saying that atoms of a different element are going to have different properties from other atoms of other elements, right? And then number 4 is kind of what we're going to get at today. And that is dealing with proportions of atoms and elements based on a certain mass and things like that. We're going to talk about that actually. That's a pretty cool concept of the law of constant proportions and multiple proportions. That's what we're going to go today eventually. But the fourth part of that theory, it says that compounds contain atoms of multiple elements and small whole number ratios. Let me show you what I'm talking about. So we'll write that down. Right, so compounds now, not elements, but compounds, which we talked about before. These are chemical compounds. These are not mixtures. These are elements or atoms of a particular element that come together and they bond chemically. They are chemically bound together. So compounds contain atoms of multiple elements. Right, in small whole number ratios. Let me get that together. Small whole number ratios. Right? So we say, let's say we have C2H6. This is the compound ethane. Right? The ratio of carbon to hydrogen is 2 to 6 or 1 to 3, right? So every compound is going to have some formula, and within that formula, those atoms of different elements are going to be in a specific ratio, right? And those ratios actually matter because it's the ratios of the atoms from different elements that give the compound its properties, right? So C2H6 is ethane. That's ethane gas, highly flammable, kind of funky smelling gas. Um, but again, that ratio is going to determine its properties. Sorry. I don't know why Apple did that. Right. So the ratio is going to uh it's going to really control the properties of a given compound, right? Depending on how many carbons, how many hydrogens, how many other atoms, it's going to determine that. All right. So those that keep that small whole number ratio idea in the back of your memory banks, because we're going to come to that shortly, right? So compounds contain atoms of multiple elements in small whole number ratios. And then the final part of Dalton's theory is that atoms are rearranged during chemical changes. Right? Atoms get rearranged during chemical changes. They do not get destroyed. They just get rearranged. Right? So anytime you do a reaction between atoms of a particular element and they come together or they react with one another, they don't get destroyed, they only get rearranged. And normally when you take atoms of a different element and you react them together, then you get compounds that have totally different properties, right? Let me give you an example. If I take calcium and chlorine, let's say react those two together, then I get calcium chloride, right? Notice there are two chlorines here. All this stuff is going to come out in the wash when we start talking about nomenclature and building expressing chemical formulas and things like that. All right. So can somebody who, if you have a periodic table close to you, can you look up, look and find what column calcium is in? Start on the left where hydrogen is and work your way over from the left to the right. Tell me if what column calcium is in.
Isn't it second?
It's in the second column. So what that means, and for practical purposes, is that calcium, and I'm gonna go ahead and introduce you to this, even though we're not gonna dive all the way into it because we still got some other stuff to talk about. But you have calcium. If it's in the second column, right, it's gonna have a charge of +2. Sorry, I'll just put 2 plus. And then chlorine. Somebody tell me what column chlorine is in. So look at in the middle, in between the first two columns, and then now you have this big block in the middle. Those are transition metals. And then once you pass through the transition metals, you go to the right. So start at B, boron, and count over and tell me what column chlorine is in. Anybody got it yet? Is it group 7?
Yes.
Yep. You see B, boron, and then you see carbon, and then nitrogen, and then oxygen, and then chlorine. So chlorine is what we call group 7. All those group 7 atoms have a charge of -1. So when we take these two things and put them together, I'm just again introducing, because there's no time like the present, even though we're going to talk a lot more about this. I'm going to take this number without the sign, and I'm going to move it here. It's called the crisscross method. That's how I know that there's 2 chlorines in that formula. So I'm going to take this number and put it here. And by the same token, I'm going to take this number and put it here. Uh-oh, sorry. All right, we call that the crisscross method. All right, that's how I know what numbers to put in for that compound, CaCl2. All right, and then what I need to do now also, which we're going to learn quite a bit about, is I need to balance this, because that ties into number 5. All right, let me add in not destroyed. Right, that's very important. Without balancing it, what does it look like on the other side? It looks like I gained 2 chlorines, but then on the left side of the arrow, how many chlorines do I have reacting with calcium?
1.
Only 1. So it looks like I created a chlorine out of nowhere, but in reality, I didn't. I have to balance this. So what I need to do is take inventory of both sides. So on the right side, I got 1 calcium and 2 chlorines. On the left side, I have 1 calcium and 1 chlorine, and I can make it right by putting a 2 here, right? Because again, I cannot just pull atoms out of thin air, nor can I destroy atoms at random. So everything has to stay balanced. So once I do that, now my equation is what we call balanced, and it's the same number of atoms on each side. So that's what so this is this 2 right here. Just stay with me. Don't jump off the boat yet. It's called my stoichiometric coefficient. That's what we call that, stoichiometric coefficient. What that does is it allows me to make sure that there's the same number of atoms on each side of the equation to keep in line with that final tenet. Which says that atoms only rearrange, they don't get destroyed nor created. Right. So that when I balance that, that takes care of that. And it keeps me in line with the theory. I don't violate the theory by just doing what I want to do. All right. Any questions about that? I know that seemed like a lot, but we're going to do a lot of balancing and a lot of chemical equations toward the end of this chapter. So don't sweat it. But sometimes it's better to introduce something than to wait, and then talk around it. And then you get to it. It's like, oh man, we've been talking about this already. So I think I like to touch stuff when it shows up instead of waiting and then keep you in suspense. And then all of a sudden we start talking about it. And then your mind, you're like, hey, we already saw this. Why didn't we talk about it then? All right. So the other point I'm making is about the rearrangement is that calcium chloride, which is on the other side of the arrow, let me write this down here. That calcium chloride is totally different from calcium and chloride separately. Properties are totally different. Totally different. And that's what when we talk about up here, that compounds contain multiple elements in small whole number ratios. The ratio of calcium to chlorine is 1 to 2. But we also understand that the ratio affects the property. So when we get this compound on the other side, it's not going to have the same properties as the atoms that came together to make it. That's the point I'm trying to make. All right. Any questions? So this is a theory which we talked about, and a theory is a body of collected knowledge that explains an observation, a very large and well sourced and well verified body of knowledge, right? That explains some observation. So this is Dalton was able to do a lot of different experiments. He was actually a physicist, not a chemist, but he was able to do a lot of different experiments to kind of determine um, the properties of atoms, when before everything was a hypothesis. Now he was able to do the experiments, and not just him by himself, but other scientists along with him, able to do those experiments to prove that that hypothesis was either right or wrong. And for the most part, they proved that yes, matter does consist of atoms. Atoms are the smallest part of an element. Atoms are indivisible, and atoms within an element all behave the same way. All right. So now let's move on and talk about a different topic. Still in this vein, but not the exact same thing. So then you had another scientist by the name of Proust, French scientist, and he developed what was called the law of constant composition, the law of constant composition. So let me get my handwriting together. Now, what is it? Let's go back and jog our memories. How do we know? How does something become a law? Not legal law, but a scientific law. How does something become a scientific law? What do we need in order to uh, classify something as a law? In other words, what does the hypothesis lack that the law doesn't?
Evidence.
Evidence. Excellent. Who was that?
Alexis.
Very good. Evidence. Data. With the hypothesis, you have no data. You just have an idea based on something you saw. It's all empirical. A law means that you have collected enough evidence to say that this hypothesis is either true or not true. All right. So the law of constant composition is it says this. It says that if you have a sample of a pure compound, uh, it doesn't matter where you take the sample from, that sample is going to contain the same elements in the same ratio by mass, right? So let me boil that down. So all samples of a pure compound will have the same elements in the same ratio or same proportion by mass. And I'll zoom out. Same elements, same ratio by mass. Right, so all samples of a pure compound, no matter where they come from, will have the same ratio of elements by mass, no matter where you take it from. If you take, in his experiment, he actually did copper carbonate, and I'll show you that in a second. But let me give you an example, right? So let's say we take a sample of water. Let's say we take a sample of water. How many hydrogen atoms are in water? Based on this,
Two.
two. Good. So we got two H's. How many oxygens?
One.
One oxygen. Right. So the ratio of hydrogens to oxygen in water is 2 to 1. Right. And then if we look at the mass, right, it's going to be 2 to 16. And I'll tell you why, or 1 to 8 if we reduce that ratio down. 2, where I get this number 2 from is from the periodic table, right? So somebody tell me on the periodic table, find hydrogen and tell me what the atomic mass of hydrogen is. All right. Let's do this. Because I want to make this plain, because again, this is something that's going to come later, but it really should be introduced now, because there's no sense in trying to talk about constant proportions and constant composition and knowing that we need the atomic mass of an atom or an element, but we don't know where that's coming from. So let me show you. If my computer will cooperate. Come on. Pull up the periodic table, or a periodic table. I need to zoom in on it. All right. Can't really see that. Let me zoom in. That's not good. Hold up. Let me find another one, because this is bad. Oh, this one might be better. Yes. But they don't have the masses. That doesn't have the masses. Let me see if this is legible. No. Come on, ACS, help us out. All right. So you can see right here, this number underneath hydrogen, 1.088. That's the atomic mass. So in essence, the hydrogen atom has an atomic mass of 1 AMU. And so that's why when I look at the mass ratio for water, the hydrogen, since there are 2 hydrogens, 2 times 1 is going to give me 2. So that's why the mass of that is 2. And then if we go over to oxygen, you can see right there, what's that number? Can y'all read that? Yeah, you gotta be able to see. What do you see there for oxygen?
16.
16. So that's why when we talk about the mass ratio is 2 to 16. Or you can reduce that down to 1 to 8, right? So when we talk about those compounds existing in whole number, small whole number ratios, that's an example. So with water, if I take a sample of water from the ocean, if I take a sample of water from my kitchen sink, if I take a sample from my toilet, if I collect rain, that ratio is going to stay constant. It's going to be 2 to 1, 2 atoms of hydrogen to 1 atom of oxygen, and the mass ratio is going to stay the same, 2 to 16 or 1 to 8. That's what that constant composition means, right? So we're going to look at, we got plenty of time. We're going to look at another example. So let's look at Proust's actual experiment that he did. Well, one of them anyway. So he took copper carbonate, and let me show you what that looks like before I switch back. So this is an example of what copper carbonate looks like. It's a kind of a light green, turquoise looking solid. And so Proust was studying copper carbonate, and this was one of the experiments he used to determine the law of constant composition. All right. So let me show you what he did. Switch my screen back to my iPad. Right. So with copper carbonate, he actually took 2 samples. Right. He took a sample from nature, natural sample, 100 grams, and then he took a sample that was a synthetic sample. So that means that he made it. He took copper and probably carbon dioxide in the presence of oxygen, and he made a sample of it. So he took a synthetic sample and a natural sample. Let me get this together. And that was also 100 grams, right? And when he heated this up, what he found out in the decomposition was that for both samples, the ratio of copper by mass to carbon to oxygen was 51.35, 9.74, and 38.91. And these are percentages. And this was the same for both samples, right? Same proportion, regardless of the source. So that law of constant composition says that all samples of a pure compound, no matter where they come from, are going to have the same ratio of elements by mass, right? So it doesn't matter if it's natural, if you make it in the lab, if you go dig it up in the backyard, you're going to have the same ratio. All right, so let's take this and apply it, because these constant composition problems, you're going to see these a lot, right? Especially in this chapter. And on Thursday, we're going to work through some more of these. I'll have, of course, when we do recitation next week, we'll be working on these types of problems. And then there's another law, the law of multiple proportions, which we're going to talk about too, if we have time today. So let's do an example. This is a strategy. So this is our strategy for constant composition problems, right? Number one, We need the atomic masses. Whatever the compound is composed of, we need the atomic masses to figure out the ratios. So we need the atomic masses. And then the second part of this is we need the mass of whatever the compound is. Right, so we need the mass of the compound and we need the atomic masses. All right, and that's our strategy. We need those two things. Now, if we get something that we can convert into mass or convert into atomic mass or whatever, then we can use that too. But we have to have the atomic masses. So let's take a sample of CO2, carbon dioxide. And let's say if we have a 12-gram sample. Right, let's say we have a sample of CO2 and there are 12 grams of carbon. So 12 grams of carbon, and we want to know how much oxygen. That's the question. So when we're talking about constant composition, if we have 12 grams of carbon in a sample, let's look at it. So first of all, what is the atomic mass of carbon? Can somebody look that up on the periodic table? Go over there, go over to the right, find boron. Carbon is to the right of boron. Anybody got it yet?
I got 12.
Good, it's 12. That's exactly right. So if my compound is CO2 and I have 12 grams of carbon, and I look at that subscript and I know that there are 2 oxygens, right? What is the atomic mass of oxygen?
16.
16. But because there are 2 in that compound, I need to multiply that by 2. So my ratio of carbon to oxygen is 32 to 12, right? That's my ratio. It's 32 to 12 or 2.67 to 1, right? So if we know that ratio, we can take that same ratio, and if we have a sample that has a different mass of carbon, we can also figure out what the mass of oxygen is in that sample. So let's do that, because it should follow the ratio, because the law of constant composition says that no matter what the sample is or where you get it from, the ratio between the atoms is going to stay the same by mass, right? So it doesn't change. And this is not a 0. I'll just put oxygen or OX so you'll know it's oxygen. All right. So let's say I have a sample with 30, and you always look for this word if. If there are 30 grams of carbon, how much oxygen is present? a sample of CO2. Right, so what we're trying to find out again is we want to keep that ratio the same. Now we can use the ratio of what we have to figure out how much oxygen is in that sample. So it's going to be 30 grams of carbon in the sample. What's the ratio for CO2 again? And we're trying to find oxygen. So we want to put oxygen in the top, 32 grams of oxygen over what? How many grams of carbon? Right, that's the established ratio. And again, it doesn't matter what the mass of the sample is. If it's CO2, and that's the compound we're dealing with, this is the ratio we use because of that law of constant composition. That's the ratio we use to figure out the mass of the other element or the other atom that's in there. So we have a 30-gram sample, right? And we want to know how much oxygen, if the sample contains 30 grams of carbon, a sample of CO2, we can figure out how much oxygen is present as well using that ratio. All right. Can somebody calculate that? Grams of carbon is going to cancel. So I'll be left with grams of oxygen. Let me bring up the old trusty.
I got 60 grams.
Okay.
I got 80 grams.
I got 82.
80 grams. 80 grams. And that's close, and that's what it should be, right? Because remember, this number 32 divided by 12 is about 2.67. So that's going to be more than 60, right? It's going to be more than, it's going to be, if it was just 2, then it would be 60, but it's 2.67. So when you take 30 times 32 and then divide it by 12, you're going to get 80 grams of oxygen. And again, this is asking about a sample of CO2. So once I know the ratio that I'm using, I can interconvert between grams of carbon or grams of oxygen, as long as I know that I use that same ratio, which is going to stay constant, because that's what the law of constant composition tells us. No matter where you get the sample from by mass, the atoms that make up that compound have to exist in the same ratio, or they do exist in the same ratio. All right, no matter where the sample comes from. Let's do another example. All right, let's say we have an example where, and is everybody following? Anybody not following? Say something. All right. All right, let's do another example. Let's say we have a pure sample of sodium fluoride. All right, and we say that we got a pure sample of sodium fluoride if the sample contains 35 grams of sodium. It's not saying that that's the mass of the sample. It's saying that the sample contains 35 grams of sodium. So the question now is how much fluorine is present. right? How many grams of fluorine do we have in that sample? Let me put my. All right, are we following? So again, the way we attack a problem like this is giving us the mass of sodium, and we want to find the mass of fluorine, and it's a pure sample, so it has to follow the rules of the law of constant composition, right? So what do I need in order to find out how much fluorine is present? What's my strategy?
Find the atomic mass of both.
Find the atomic, excellent. Find both atomic masses. And then what do I do after that? I can set up a ratio, can I? Right, because once I know the atomic masses, then I'm able to set that ratio up. So let's do it. So we have sodium, which has an atomic mass of 23. You can look that up on the periodic table. And then we have fluorine, which has an atomic mass of 19. Right? So what is my ratio of sodium to fluorine in any pure substance based on the atomic masses? This is the ratio, isn't it? So any pure substance based on the atomic masses is going to be, the ratio is going to be 23 to 19 for fluorine, right? And sodium. So any pure sample of sodium fluoride is going to follow this ratio, 23 to 19. So now we know our ratio. We know that that ratio is constant regardless of where the sample comes from. So now we can find out, we can use that ratio to find out how much fluorine is present, right? So we said we have 35 grams at 35 grams of sodium. Is that right? And then what do I want to put in the top? What am I looking for? Am I looking for sodium or fluorine?
Fluorine.
The question asks how much fluorine is present. So with that ratio, I want to put fluorine in the top. Grams of Na are going to cancel. Is that right? I'm sorry.
For the denominator, would it not be 23?
23. Yeah, thank you for catching that. Yep, thank you. So 19 grams fluorine, 23 grams sodium. Grams of sodium is going to cancel, and I'm left with what? Somebody calculate that real quick. Is that right? Did anybody else get 28.9?
I did.
All right. So what's the purpose of this? Again, we are able, if the law of constant proportion says that regardless of where your sample comes from, if it's a pure sample of a compound, any compound, then there is a specific ratio of atoms within that compound, and it's going to be constant no matter where you get the sample from. You can take a sample from Mars, you can take a sample from Jupiter. If I take a sample of sodium fluoride from Venus and I take a sample from Earth, when I find the ratio of the atomic masses, that ratio is going to be constant no matter where that sample comes from, right? So that's the purpose of doing this. That ratio is always going to be constant, and it'll always apply to this compound, 23 to 19. for the carbon dioxide, that ratio of 32 to 12, oxygen to carbon is always going to apply for samples of carbon dioxide. So any sample of a compound is going to have a specific ratio and it's going to be constant no matter where it comes from. All right. We're going to look at this. We'll look at some more examples of this. And then we're going to look at on Monday, we'll look at the law of multiple proportions, because it's a different animal, because some compounds are able to come together in more than one way with the same two atoms or same atoms. Like if you have 2 or 3 atoms that make a compound, those atoms can combine in different ways, so they give you different compounds. So we're going to talk about that on Monday, God willing. All right. Any questions about anything before we log out? All right. Let me stop sharing and stop recording.